So today we're doing a bit of cleanup work. There's a couple of ideas. There's actually 3 things we're going to talk about today. We should get through most of it. And once we're done, then we're ready for the exam, in theory. Okay. So the first thing is a notational thing. And this is something which I'm not encouraging you to adapt necessarily, but just be aware of it. So there's this idea that we can use a symbol. We're introducing a new symbol. It uses the capital letter D. And it's a stand-in for saying take the derivative of something with respect to your variable. So normally we think of it as the derivative with respect to x. And so the fancy word is differential operator, which is just saying take a derivative. And so there's a couple of things. So what that means is if I put something, so for example, if I have the symbol d followed by x squared, what does that become? 2x. Because it says take the derivative of x squared, which is the derivative of x squared is 2x. Now, if you like, you can put parentheses. You don't need to. It means the same thing. So whatever follows that symbol d, it says take the derivative of that. Now, order makes a slight difference. So this is not the same as x squared times d. Because x squared times d says, well, you still have to take the derivative of something, and then after you found that derivative, multiply it by x squared. So order matters with this. It's one of those sort of annoying things that people might forget about. But mostly, why do we like this? Well, it helps us to rewrite differential equations. So suppose we have something like y double prime minus 5y prime plus 4y. Well, we can say, hey, how can I think of y double prime? That's the same as applying this differential operator twice. I took 2 derivatives. So it's like d times d, or d squared y. And then y prime, d times y, and y, well, that's y. And now we can start to work with these expressions, basically doing some algebra, and say, oh, we get polynomials showing up. Polynomials that involve d. And we work with them as we would with any polynomial. So we can do things like factor, we can do things like expand. And so we have our differential equation, all right, replacing it with this new symbols, and pull out the y. And we pull them out to the right, because order matters. That's what we talked about up here. So we say, okay, this differential equation really says, for your function y, throw it into this machinery. We take the second derivative of it, minus 5 times the first derivative, plus 4 times the original function. Let's say, look, this looks like a polynomial, so you can do stuff with polynomials. For example, you can factor. This one happens to factor as d minus 4 times d minus 1. But it doesn't matter which order I factor. D minus 4 times d minus 1 is the same as d minus 1 times d minus 4. Now, if we had a differential equation, which we do need one small other piece, which is, okay, we set this equal to 0, then what we can say is, well, what we really need to look for are solutions to these smaller pieces. So there's one differential equation that says d minus 1 times y. And then there's a second differential equation, d minus 4 times y, depending upon which order we take it. And say, look, if I can find something which makes that 0 or makes that 0, I found a solution to my original differential equation. Because once I have 0, 0 times anything is 0. And that's the power of the 0. So that's the idea. Now we're going to use this to do one thing. And what are we doing to do? So suppose we have a function that has the form u of x e to the alpha x. And for sanity, I'm going to write this as u e to the alpha x from here on out. So just remember u is a function of x. And now what I'm going to do is I'm going to say, well, suppose we take d minus alpha to some power and we multiply it by this function y. What comes out? Now, if we were to think of this as being a differential equation where we set this equal to 0, let's talk about what would the roots be. Now, you might say, that seems hard, Steve, but come back over to here. This d squared minus 5d plus 4, what does it remind us of? Have you seen anything like it?
This is like the
Yeah, it's the same polynomial, but what we've done is we've replaced r by d. So it's r squared minus 5r plus 4. Now, here r and d represent very, very different types of objects, but still it's the same polynomial at the end of the day. So if we were thinking of this as a differential equation, we say, well, look, this really would be something where I have r minus alpha to the k equals 0. So what are the roots of this polynomial? What makes this true? Alpha. How many times? K times. So this is saying, hey, let's dig into what's happening when we have repeated roots. So this is sort of the justification for why do we bump up in this particular way? Why does this multiplying by x actually work? So that's going to be the punchline at the end. So let's start with a really easy case. K equals 0. Well, that says we have d minus alpha to the 0, y. Well, that's just y, which is u e to the alpha x. All right, didn't have to work too hard on that one. Let's go to k equals 1. So that's d minus alpha y. Well, we can distribute through. So we're multiply the y through, keeping track of the order. dy minus alpha y. So this is d u e to the alpha x minus alpha u e to the alpha x. All right, so we need to take the derivative. What rule do we need to take the derivative of u times e to the alpha x? Product rule. Okay, so what do we end up with? Okay, u prime e to the alpha x plus alpha u e to the alpha x. And we're going to subtract alpha u e to the alpha x. And what do you notice? Yeah, almost as if it had been meant to happen, because it was meant to happen. That's good. So u prime e to the alpha x. So don't do anything. You have u to the e to the alpha x. Take one derivative, you have u prime e to the alpha x. Let's do another one. Okay, so k equals 2. So that's d minus alpha squared times y. So again, this is a differential equation which corresponds to alpha being a repeated root 2 times. That's what that notation means. All right. Well, that's the same as d minus alpha times d minus alpha times y. Right? Because square something just repeats it. Do we know what d minus alpha y is? Yeah, we know it because we just did it. So it's d minus alpha u prime e to the alpha x. Okay, so we keep going. So this is going to be d times u prime e to the alpha x. And I should say times is very loose here. This should really say d applied to, but that's all right. We all know what we mean. We're among friends here. We're all friendly. Alpha u prime e to the alpha x. Okay, take this derivative. What do we get? U double prime e to the alpha x plus alpha times u prime e to the alpha x. And that's the derivative product rule minus alpha u prime e to the alpha x. What do you notice? Cancellation again. What? Again? That's so cool. All right. So we end up with u double prime e to the alpha x. And now this is when we start putting on our like, wait a second. I think I see a pattern. When we did nothing. we had u e to the alpha x. And this is like no derivatives to u. When we had k equals 1, we had one derivative, u prime e to the alpha x. When we had k equals 2, two derivatives, u double prime e to the alpha x. What's going to happen? Well, the question is, should we expect anything to happen? What should k equals 3 do? Can you see it? It'll be u triple prime. And the reason is because if you compare k equals 1 versus k equals 2, it's the same computation other than we added a prime. That was it. Everything else is the same. So therefore, every time we go and add another layer, we just add another prime. So in general, what is d minus alpha to the k times y?
U to the k e alpha x?
Yeah, the kth derivative of u e to the alpha x. Now, at this point, you're probably saying, okay, so how does this answer our question about why bumping works the way it works? Well, remember how we said you should add this 0? So we should set this equal to 0. So we have this kth derivative of u times e to the alpha x equals 0. Well, can e to the alpha x be the part that gives us 0? No. So what has to be 0? Yeah, so that says, hey, I have some functions such that when I take the kth derivative, I get 0 out. All right, so what kind of function, when you take lots of derivatives, ends up being 0? Like just in general, what kind of function after you take enough derivatives becomes 0? Polynomials. That's the nice thing about polynomials. You take enough derivatives of a polynomial, you get to 0. Now, the question is, okay, we have to be careful. We only get to take k derivatives. How high up can we get in our polynomial? Like, what's the largest degree we can have? K minus 1. So just think of it, if you're not convinced, if I have one derivative, what makes one derivative become 0? What kind of thing? A constant. That's like a 0th degree polynomial. If I have two derivatives, I can go up to x. Three derivatives, I can go up to x squared. So that tells us, oh, this function has the form some constant x to k minus 1 plus some constant x to k minus 2 all the way down to just a constant at the end. And we're after solutions. So our solutions look like this times e to the alpha x. And so what we've done is we've said, hey, anything that looks like a polynomial times a polynomial times e to the alpha x works as long as the degree is at most x to the k minus 1. So we say, okay, one solution is just e to the alpha x, that's the last piece. Another solution would be x e to the alpha x, that's the next part, all the way up to x to the k minus 1 e to the alpha x. So this is the justification that says, yeah, it actually works the way we claimed it worked from last time. Bumping works. So that's a nice explanation. All right, any questions on this part? This is our first topic. 3 topics today. 3 for the price of 1. Great. On to our next one. So, non-homogeneous differential equations. Now, before I even start here, let me just say there's going to be a big focus on non-homogeneous differential equations after our next exam. So, don't stress too much about it now. You'll have plenty of time to stress about it later. But I just want to say what the idea is. So, what makes something non-homogeneous? So, if I looked at this differential equation, which part is the non-homogeneous part? The f of x part. So non-homogeneous says, hey, I have something on that right-hand side. The homogeneous part would be if I set that whole thing equal to 0. Now the goal is, well, how do we go about solving these? Because we've talked about how do we solve homogeneous differential equations. We have sort of this philosophy. Find a bunch of solutions which are linearly independent and look at linear combinations. So the question is, how do we handle something that's non-homogeneous? And it turns out it's not too bad. There's just sort of, at the end of the day, there's more or less one extra step. So here's the extra step. It says, look, first off, find one single solution, any single solution at all, which satisfies this differential equation. And we're going to call this y sub p. So here, what is y sub p? Well, p stands for a particular solution. Say, I just want to find one function that works for this differential equation. Now you might say, wait a second. When we're looking for general form, that says we're looking for all of the functions. That's what we mean when we talk about general form, all solutions. And you're telling me you only have to find one? In this step, yes. Okay, so find one solution. Now, you might say, how do we find it? For right now, it's handed to us on a platter. And they said, look at this beautiful function. It works. Check it. Later on, we'll say, we'll actually find it ourselves. We don't need that fancy platter anymore. Okay, the next step says, okay, now we're going to take this differential equation and we're going to change one thing. And the one thing we're going to change is that we're going to make it homogeneous. So in other words, the left-hand side is still the same, but we set it equal to 0. Say, all right, so this is the corresponding homogeneous differential equation. Say, all right, there we go. We have technology in certain cases. In particular, if we have constant coefficients, we know how to solve this. And so we solve it. And we're going to come up with a general solution. And here, we would have our general form has the form some constant y1, some constant y2, all the way up to some constant yn. So this is the general form for the homogeneous part. And we call that y sub c. C for the complementary solution. All right, so finally, what do we do? Well, the answer is we put them together. So we take that one function, which solves the non-homogeneous part, and then we add the general thing that solves the homogeneous part. And we say, aha, this works. This will do it. Let's sort of take a few seconds to try to convince ourselves, yeah, this makes sense, it'll work. So first off, because we're adding them together, and this is a linear differential equation, what we can do is we can say, let's plug both pieces into the differential equation and see what happens. If I plug y sub p into this differential equation, what comes out? So I'm plugging y sub p into the left-hand side. What comes out? It equals f of x, because that's what it means to be a particular solution. It actually solves the equation, so we get f of x. What happens when we plug in that complementary part, that yc, into our differential equation? Again, we're plugging it into the left-hand side, but it's the same as this left-hand side. What comes out? 0. And now we're going to use a very cool fact that says, if I take f of x plus 0, what comes out? F of x. And therefore, the whole thing, by adding on that complementary part, we still have a valid solution. But here's the nice part. We say, okay, this is a valid solution regardless of what I pick for my complementary piece. Well, my complementary piece, how many choices do I get to make? Well, in other words, how many constants do we have? That's our number of choices. Well, yeah, so we get n constants. That means we get n choices. We could say we have n degrees of freedom. That's enough freedom for us to solve. And so we can satisfy any initial conditions. And I'm going to say something very vague and not super precise, and then we're going to do an example and say, oh, yeah, that's what I meant when I was saying something vague and very unprecise. It's when we're trying to satisfy an initial condition for this format, where we have y sub p plus yc. So in other words, when we're trying to find a specific solution to a non-homogeneous differential equation, it turns out it's equivalent to solving a solution for a homogeneous equation where we slightly tweak the initial conditions. And we know that we can solve that because we've come up with a set of linearly independent solutions. So therefore, we will have success. Or as the Klingons say, kapla, which of course we all know is Klingon for success. Kapla! All right. So, are you ready? Should we try an example? Okay. Here we go. Here we go. For the differential equation, y double prime minus 2y prime minus 3y equals 27x squared. Verify that this function, it's a polynomial, negative 9x squared plus 12x minus 14, is a solution. And it also says find the solution with y of 0 satisfying something and y prime of 0 satisfying something. That means we get to make some choices here. Okay, I think we'll have one of them be 6. Is there another choice? Did someone say factorial? Wow. All right, we'll go with 7. Okay, 6 and 7. All right, so that's our goal. Now, based on the discussion we just had, this function right here, we were giving another name just a moment ago. Do you remember what we were calling this? Yeah, this is our particular solution. This is our y sub p. All right. Well, but we know how to verify something as a differential equation. So we verify. And we begin. Here we go. So we're going to take minus 9x squared plus 12x minus 14. Second derivative of that, minus 2, minus 9x squared plus 12x minus 14. The first derivative of that, minus 3 times minus 9x squared plus 12x minus 14. Okay, so we're going to take some derivatives here. Well, we'll have something here, minus 2 times something there, and minus 3 times, well, the function. That's easy to do. The function's just copy. What's the first derivative? Negative 18x and plus 12. Okay, once you have the first derivative, the second derivative, keep going. What's the second derivative? Negative 18. All right. So now what we'll do is we'll carefully expand. And the reason I emphasize the word carefully is we don't want to lose any points. Our goal, get all the points, all the points. So in particular, remember that these are going to distribute through here when we multiply through. Parentheses are wonderful tools for saving points. All right, so I have the minus 18. Here, minus 2 times minus 18x, 36x. Minus 2 times 12, minus 24. All right. In case you're wondering what I'm doing here, I want to write the constants in a column, the x's in a column, and the x squareds in a column. Minus 3 times minus 9x squared, 27x squared. Minus 3 times 12x, minus 36x. Minus 3 times minus 14, it's the answer to life, the universe, everything. 42. 42. You're probably thinking, wait, that's the answer. What's the question? They're still working on that. All right. So let's see what happens. 27x squared, well, that's only x squared, so that's going to be 27x squared. That's a good sign. 36x, subtract 36x. 0. Minus 18, minus 24, plus 42. Yeah, so 18 and 24 combined get it to 42, but of course negative 42, positive 42 is 0. And then we say, okay, so when we plug that function in, we got 27x squared out. We were supposed to get 27x squared, which means, kapla, success. We've done it. Verified. Okay. Good. So no surprise there. We know how to verify differential equations. All right. On to the next part of the problem. So we have a solution. We have our particular solution. If we're finding a particular solution in general for this differential equation, what is the next thing we're going to need to do? Find the complementary solution, which means we're going to switch to a new differential equation. It's not going to be so new. The only thing that happens is we change the right-hand side to 0. All right. So we have this semi-new differential equation. Y double prime minus 2y prime minus 3y equals 0. And we're going to solve this. What's the process? What comes next? Put in the r's. Yes. So what do we have? R squared and minus 2r and negative 3 equals 0. All right, we need to solve for r. Someone just said, aha, r is these two values. Okay. But we'll do that a little bit slower. Can we factor here? Yes. What does it factor as? R minus 3, r plus 1. Now, if you're skeptical, check. R squared, that's right, plus r minus 3r, minus 2r, and minus 3 times 1 is minus 3. It's always good to check yourself, you know. There's, as they say in mathematics, you should check yourself before you wreck yourself. So make sure. Check your work. Check your work. So what are our roots? What choices for r do we need? Yeah, 3 and negative 1. And this is like, oh, beautiful numbers. They're distinct. They're real. Very straightforward. So our solution for our homogeneous part, which I'll write y sub c, looks like some constant, let's say a, e to the 3t, plus some other constant b, e to the minus t, which is really minus 1 times t. All right, so that's the complementary solution. Now we put it together and say, okay, so solutions to our differential equation in general look like our particular solution. And so I'll write that, minus 9x squared plus 12x minus 14. Plus the complementary solution, a e to the 3t plus b e to the minus t. Now these parentheses aren't necessarily needed. I'm just using them to help emphasize here are the pieces. So we can say, oh yeah, that came from, oh yeah, I see where the pieces came from. I got you. I'm with you. I'm with you. All right, so we now have the general form for solutions for this differential equation, which is great. So where do we go next? Yeah, so we got to use the initial conditions. And so one initial condition uses just the function, which is great, but one of them uses y prime. So we should write down y prime. Now the good news is we did y prime of the particular solution. So that's minus 18x plus 12. What's the derivative of this piece? 3a e to 3t and? Minus b e to negative t. Wonderful. Wonderful. All right, so time to plug it in. So we plug in y of 0. What do we get? Negative 14. 0 is a nice number, so, you know. And then what was the other parts? A and B. And that should equal 6. Y prime is 0 is 12, because you have that. Okay, and what else? 3a minus b. And that will equal 7. All right. Okay, so great. We can do this. And first off, I'm going to move these constants, negative 14 and 12, to the other side. And so that becomes a plus b equals 20. 3a minus b equals 7 minus 12, negative 5. All right, that's not the worst set of numbers I've ever had to work with. I've seen worse. Okay, so I'm going to try to do a quick callback to a vague thing I said before. If this doesn't process, you can just be like, Steve's talking crazy right now. I don't need to worry about it. Remember I said that, how do I know we can solve? Well, see, we know we can solve in our homogeneous solution any choices for inputs for initial conditions. Because that's the whole point. When we have a nice full set of solutions, we can solve any initial conditions. Life is good. So what happens? Well, see, we thought our initial conditions were 6 and 7, but secretly, it's like going back to our homogeneous saying, oh, if we can solve for 20 and negative 5 for our initial conditions. And so we know we can't in our homogeneous part. Because the homogeneous says, I can solve anything. I'm great. So that's why we know we can succeed. Okay, 2 equations, 2 unknowns. This is our bread and butter. We got to get good at this. What can we do to help us solve? Eliminate a variable. How can we do a quick elimination? Add. Add the left-hand sides together. What comes out? What comes out on the right-hand side? 4a equals 15. So that was pretty quick. What is a? 15 over 4. Now, well, let's plug it into the first equation. 15 over 4 plus b equals 20. But let's put 20 as something over 4. What does that become? 80. So 80 over 4. So what is b? Yeah, so 80 subtract 15 makes 65. All right. So now we're almost there. We found a and b. We have our form. We just need to put it all together. So y equals minus 9x squared plus 12x minus 14. And then plus a, which is 15 fourths e to the 3t. And then plus b, so that's plus 65 fourths e to the minus t. And we're done. That's it. That's it. Okay, so that's how you handle homogeneous differential equations. At this stage, they will give you the particular solution. But other than that, it's very similar to things that we've already done. Any questions? Oh, you're right. Why did I switch to x's, to t's? What are you talking about? They're all x's. I don't see any t's there. I think t was in anticipation of our third topic for today. Yes. Spring mass systems. Yeah. Yes, I can feel the excitement in the air. Oh, yes. I love these. Great. I'm glad that you're enthusiastic. This will make it easier. Now, these have a few different names. Sometimes you'll see something spring mass, dash pot, spring mass damper. A dash pot and a damper are basically the same thing. So there's something that is trying to slow you down. So you should think of it in the following way. You have some sort of fixed surface. You have some object with a particular mass attached to it. And there's 2 things. There's a spring, and springs like to be springy. We know what springs like to do. They like to go up and down, especially if you start them. Then there's something else. There's a damper. And dampers like to sort of rain on the parade. Say, no, come on, slow it down, calm down. We want to be back to where we were. Now, they're both important. So, for instance, you can imagine you were driving a car. And in cars, you have some things called a suspension. And you want a suspension because that helps you survive if you drive over a pothole. If you didn't have it, that would hurt. So you want that. It's essentially a big spring. It helps to lessen the blow, makes it a little softer. Now the problem is, what if you only had suspension? Okay, well, if you set that spring in motion, it's going to keep being springy, and your car's going to keep going up and down for a very long time. So you have to have something to balance it. So you also have shocks that say, okay, if you start having a motion up and down, we're going to help dampen that and bring it back down to a stable form. Combining those 2, you can get very comfortable cars. Now, how does this work? Well, it turns out it's not too bad. So for a spring, this is something we talked about on day 1. Do you know what this is called? Hooke's law. So Hooke's law says, hey, the farther you pull a spring, the more it wants to return to where you started. And by that, we say, you can imagine that there's some sort of measurement we think of like there's x equals 0. So if you pull this up, the spring says, no, come back the other direction. And the more you pull it up, the more it says, no, I'm serious, you really need to go back. So that's what Hooke's law says. So the force is related to how far you pull it. Now the damper works in a different way. It's not based on how far you've pulled it, but rather how fast the object is moving. So in terms of like a physical damper, you can imagine that there's a plate in some viscous fluid. And so that as you push it through the fluid, there's more resistance the faster you try to push it. So now the force is not based on distance, it's based on speed. So that's the damper. So the spring based on location, distance, damper based on velocity or speed. And that's the two forces. Okay. So now we say, well, what's happening to this object where the mass is? Well, we add up the forces. All right. So the force, well, we know how to find a force for an object. It's mass times acceleration, mx double prime. We add the spring, what the spring is doing, that's minus kx. We add the damper, that's minus some constant x prime. And then we have anything else. And anything else we put in and say there's an external thing happening. So maybe there's some other object acting on that mass which is causing it to move. Now, as we go on in the semester, we'll get more into details about things we can do. I anticipate that sometime in the semester, we'll get to talk about, well, what happens if you hit it with a sledgehammer? We'll get to that technology later, the sledgehammer technology. But we're not ready for that yet. We got to work our way up to it. So now we just rearrange. So we have mass times the acceleration. That's the force. Combine that with the force coming from the damper, the force coming from the spring is equal to the F of t. And this F of t, just want to say, is the external part. For what we're going to talk about today, we're not going to worry about F of t. So we're not going to do anything non-homogeneous. So we're just going to be focusing mx double prime plus cx prime plus kx equals 0. All right. And basically that's it for us. Once we understand that's the model, then we say, hey, that's a second order differential equation. Constant coefficients, linear. We love these. This is great. So let's do one. An example. Analyze a spring mass system with no external forces. So, okay, this side is going to be 0. Where m equals 2, c equals 12, k equals 50. And there's some initial conditions. We say initially, so this little x naught is the initial position, it's 0, so there's no offset. But also x prime is 0, we can think of it as the initial velocity, v naught, is negative a. So it might be no offset, but there's some speed attached to it. Okay. Now it's a little bit vague about what analyzed means. So let's say analyze says, let's find the function, and if we have any shot, let's try to graph it if we can. I don't know if we can, but we should try. So, but we can definitely find it. I believe in us. Our powers combined, we can solve this problem. What's the first step for us to solve this problem? Yeah, we have the pieces. So let's just put in these numbers into our equation. Okay, so 2x double prime plus 12x prime plus 50x equals 0. That was pretty quick. Now where to? Okay. So turn it to the characteristic equation, or the auxiliary equation, 2r squared plus 12r plus 50 equals 0. Now, let's just notice we can divide everything by 2 to make life a little bit easier. Okay, so what do we do with r squared plus 6r plus 25 equals 0? All right, so we have a vote for quadratic formula. Now, we've already done quadratic formula, so we're going to do something different. And you're probably thinking, no, I don't want a factor. We're not doing that either. So this is another third thing you can do. So let's start with r squared plus 6r. And we say to ourselves, boy, you know, there's one thing I really love. I love squares. I want to make this a square. it feels somewhat incomplete. So I'd like to somehow complete the square. So what can I do to r squared plus 6r so that I have a square? Plus 9. All right, now for those who are wondering, where's the plus 9? Well, the r squared coefficient is 1. That's important for what we're about to do. Take the 6 and divide by 2. 6 divided by 2 is 3. Then you take that new number and you square it, and that's what you add here. And this number in particular is r plus 3 squared. And you might say, Steve, can you do that? And yes, because I haven't finished writing stuff down. Okay, so I've added 9, but I need to get up to plus 25. How short up am I? I'm 16, so I'll add 16 more. Then I'm okay. So r plus 3 squared plus 16 equals 0. All right, what does that say about r plus 3 squared? Negative 16. Take the square roots. R plus 3 will be 4i plus or minus. Yeah, there's two possibilities. So finally, what are the roots? Yeah, negative 3 plus or minus 4i. All right. Good. So now we've got complex roots. We learned how to deal with complex roots. We did that last time. We have memory. We remember stuff. Okay. There's some skeptical people now. I don't think we have memory, Steve. No, I think you do. Okay, so let's write down the general form. So we have some constant. I'll say a. What's the function? Oh, whoops, I shouldn't use y. I should use x. We have x equals, because x is the name of our function. Sorry, what? Oh, someone wants to do e to the negative 3 plus 4i. No, we're keeping it real in this class. We're keeping it real. Okay, how do we keep it real? What's the function? I'll give you a hint. Negative 3 is the right thing to put here. What comes next after the negative 3? T. Okay, and then? Cosine. Plus b e to the negative 3t sine. So the real piece of it, which is the negative 3, that's what goes up in the exponent. The 4 is what goes inside the trig functions. So that's why you see the e to the minus 3t's, and that's why you see the cosine 4t, sine 4t. All right, let's throw in our first initial condition. Okay, when we plug in x of 0, what do we get? So we're plugging in t equals 0, what do we get? A? Are you asking me like, oh, what is that, A? Oh, yeah, A. Oh, sure, A. Oh, yeah, A. Yeah, it's A. What about the B? There is no B because we're going to get 0. Now, what do we know about x at 0? It's 0. That piece goes away. It's gone. Pow! Nice. Okay. So you are allowed, by the way, to update your equations as you say, oh, now I know what this piece is. I know what that piece is. That's allowed. No problems. No problems at all. Okay, now we need x prime. But the good news is we only need to take the x prime of the piece that's left. Do you trust me? Wow. That's amazing. After all these times when but I'm glad you do. So minus 3b e to the minus 3t sine 4t. That's if we take the derivative of the e to the minus 3t, leave the sine 4t alone. Now the derivative of sine is cosine, and then don't forget the 4. So plus 4b e to the minus 3t cosine 4t. Okay, so we plug in 0. What comes out? 4 times b. The sine part goes away. And this should equal negative 8. So what is b? B is negative 2. So our solution is minus 2 e to the minus 3t sine of 4t. Okay, so we found it. Now I'm pretty confident that we can make at least a good attempt to see what this looks like. Now, if you covered up the e to the minus 3t and you just saw the sine, do we know what that looks like? Yeah, it looks like a sine curve because it's a sine curve. It goes up and down, up and down, up and down. And there we go. So just sine of 4t, well, the trick is it's going to go between plus 1 and minus 1. And it does something like that. Okay. So the question is, well, what does this do? And the answer is, do you know what this does? I guess I should ask. So yeah, it's going to cause things to shrink. Now what you do is you say, take this function, don't worry about the minus. So I have 2e to minus 3t. So I'm going to graph that roughly. That's an exponential function. It's going to go down towards 0. So here's 2e to the minus 3t. And then I'm going to graph the negative of that. Okay, so there's minus 2e to the minus 3t. And now what happens is the sign doesn't go between plus 1 and minus 1. It's going to go between these two curves. So it's going to go up and down between them. And that's it. Now, one quick question. Am I going to come up initially, or am I going to come down initially? Yeah, that's the negative that does that. So we oscillate between these two. So this is an example where we have damping going on, where as time goes forward, it's going to shrink down. Now, it's supposed to be equally spaced, so you can imagine I was a better artist, but that's the idea. All right, the last part we're going to talk about today is this nice wall of text. Whoa. And it sounds like, whoa, that's a lot of information. That's okay. We'll go walk through it quickly. You can look at it in the notes. So the question is, what kind of behaviors can we have? Well, it all comes down to saying, look, we know what our differential equation looks like. We know it has to have that form, mx double prime plus cx prime plus k equals 0, because there's no external force. We also know that because these constants are always greater than or equal to 0, that says that all the roots have to be negative in their real parts. Okay, so what can happen? Well, one thing that can happen is that we forgot to install the damper. So it's undamped. So that says you look like that. Well, that's what we know. So this is our c equals 0 case. And it looks like a sine curve. And there we go. Now the roots of this, by the way, are pure imaginary. Kind of reminds you of the song. Come with me and you'll be in a land of pure imagination. Right? Right? Yeah. Okay. All right. So there's that case. Now, what happens as we start to turn the dampening up? Well, if there's not a lot of damping, we say it's underdamped. There's not enough damping going on. And so you see the sort of exponential decay. So that's the case where you have these sort of complex roots, negative I plus minus bi. If you turn your damping up a lot, we say it's overdamped. It's like, whoa, you installed too many of these shock absorbers, way too much. And what happens is you install so many that your roots are no longer complex numbers, they're real numbers. So you look like some combination of two exponential functions which have decay. We call that overdamped. And the critically damped says you're right on the borderline between being underdamped and being overdamped. Now, it's not too hard to show. The critical damped is when c squared is equal to 4mk. Underdamped is when c squared is between 4mk. I know how to spell 4mk. I do. C squared is between 0 and 4mk. And here, c squared is greater than 4mk. So these are the types of behaviors. Now, you might say, do we really need to know this information? Yes. You should. You should. All right. We'll stop there.